I didn't mention this last time, but we're recording all the lectures. It's just an iPad screen recording, and that's why I wear these headphones. Is just to upload my voice to YouTube afterwards. Your voices will not get recorded, picked up on my headphones, so you don't have to worry about that. And I usually do it like end of the week, maybe everything for the week. But you already see like last year's lectures and stuff already up, so I think this is not so surprising. Okay. All right. Okay, so today we'll do our first lecture about hashing and kind of an interesting application of it. At least it was new to me when I was in your position. But first, I promised, and we can do this next class as well, because I didn't really give full time to go through the syllabus slowly. Any time to answer any questions about the syllabus. I got our grade scope synced up to Brightspace, so maybe many of you were added to the grade scope automatically. But yeah, any questions? Okay, fine by me. I'll show this again next time in case you suddenly get super excited about the syllabus. Okay, so let me just we did a lot last class. So I'll just briefly remind us, in addition to the kind of definitions of Stanford standard probability stuff, we focused on three applications, really two. Three stat quick sort, quick select. So three stat, this is just you're given a formula, and maybe compare it to what you had done in your previous undergraduate algorithms class or something. We had shifted focus to trying to approximate stat formulas and trying to get as many clauses as possible. And we studied this kind of like utmost naive algorithm where you flip a coin for every variable. Yeah, and and really the theme of that was that there's a hard way to do it, or kind of impossibly hard way to do it, and then there's an easy way based on linearity of expectation. Yeah, and somehow the stat is supposed to represent some very complex thing, right? Like as simple as it looks, like we have no algorithms for it, but somehow you just do linear of expectation. You focus on one clause at a time. It's actually quite easy. The other thing we did, which was kind of clever, was taking that completely random algorithm and making it deterministic. Uh, by using this kind of method of conditional expectations. So once I knew that I had some kind of theoretical experiment that's always guaranteed to get 7/8 of the clauses, then I could just start conditioning, saying, well, okay, I know that a random coin toss is pretty good. So one of the two, if I fix it to be heads or if I fix it to be tails, the remaining experiment should still be pretty good. And the great thing is, linear expectation makes things so simple. You can actually calculate conditioning on this, what do I expect to get? Conditioning on that, what do I expect to get? So you turn this into a relatively straightforward algorithm where you just say, okay. Yeah, so suddenly you get 7/8, and then what's amazing is that that's the best you can do unless P equals NP. Okay, the other thing we did, which I know that you had all seen this algorithm probably before, was quick sort. Okay, so that's kind of a very intuitive sorting algorithm. If you want to sort a bunch of things, you pick a random one, you compare a thing, divide into two halves, bigger, smaller, recurse. Yeah. That too, I actually didn't do a great job of. I mean, I didn't give it all the time I probably should have because we spent more time than expected on SAT. Uh, but there's a hard way to analyze this that didn't kind of take us down. And there's a cleaner way, or if you just focus on for every two elements whether or not they're getting compared, and that's kind of not so bad to analyze. These two get compared only if it gets picked before any pivot in the middle. Then you can analyze the whole algorithm rather cleanly. So again, linear expectation, this very simple thing, it's not hard to prove, does so much work for us. So much work. We also showed high probability bound. Okay, but I know that time was running out and half of you were probably asleep. That's okay. We'll get more practice with that stuff later. Okay, so today I want to talk about this application called heavy hitters and frequency estimation. And each class will do an algorithm and it may introduce some techniques. The main technique we'll introduce today is hash functions. We'll also use Markov's inequality, but you saw that a little bit last class. Okay, so who's seen this page before? It changes like every year, but okay. So this is a Google Trends. and this was like Google Trends as of an hour ago. And apparently, there's someone named. Anyone here follow tennis? Got one headband in the back. Okay. Uh, and a tennis player. Okay. So I guess. Does anyone know what happened to Taylor Townsend today? I don't. Is this the wrong class to be asking? Yes, it's the wrong class. Okay. Okay. So anyway, so Google Trends, it's a website, and among the fun things it does is it'll list kind of the trending stuff at any given moment in time. So today we have Taylor Townsend. This is always where I find out I'm really old. There's Taylor Townsend, Suzanne Monarez. I guess you get hints from this trend breakdown. So I think she was the lady who resigned today from the CDC, or resigned yesterday. That- oh, she got okay. Anyway, exciting stuff. French Montana, apparently in connection to the Princess of Dubai. I don't know. Some lottery stuff, NFL jerseys, I guess. Uh, Katie Slayton, something happened to her. It says 1,000-pound sister's death, so that's not good. Uh, and then of course the school shooting, and then I don't know who. Okay, I don't know who Mega Hawlucha is, but okay. Sorry. Oh, should I know who that is? Wait. This person is a Pokemon? Okay. Well, maybe we should revisit this list. Is Richie Torres also a Pokemon? Back in my day, it was only 150. It was much easier. Okay. Anyway, so they have this website. Okay. So, okay. So why do they have this website? Uh, well, it's for fun. Uh, but also why does Google want to track all these most popular queries? It's for caching, right? Why is Google like so fast? Why does it seem to have the answer before you ask it? Because it has the answer before you ask it, right? Because your beloved personal question is probably one of a million people at the same time. Okay, so what it's going to do is it's going to try to keep track of the queries that occur more frequently than just random, and just save the answer instead of researching the whole web every time, right? Okay, so it needs to do some kind of some analysis just for caching, and that's how you get this kind of faster than computation latencies. It's just a lookup. But the real question is how, right? Because there's so many possible queries out there, right? Any, I guess, combination of sentences or Pokemon apparently constitutes a query. And there's just too many queries to just have like a counter for every single one. Okay. So somehow you want to try to count all the queries, except you can't really count all the queries. Okay, so that's sort of the high level situation we're in today. Okay? And you can imagine any number of services are in a similar situation. Okay, so our model that we'll look at is called a streaming model. Okay, so this is the idea that like the data that you're dealing with is kind of way bigger than your computer. Okay, and we'll look at a kind of clean version. So here you're going to have elements that come one at a time in like a stream. Okay, and you're going to think of yourself as like a very small computer that's just kind of processing one element at a time. It sees the next element, and then you save a little data locally. You make some updates, and then you see the next element. You see the next element. You might have space to hold, I don't know, 10 elements, squared elements. I don't know. Um, okay, but in general, it's not a situation where you can look through the data, do some crunching, and then look through the data again, right? Like we do with graph algorithms or something. Okay, it's this idea that data's coming in. It's so big that it's going to be lost once you're done processing it. Okay. And our question is sort of the heavy hitters problem. 5% is arbitrary here. But the question is, okay, out of this stream of elements, what are all the elements that occur at least, say, 5% of the time? 1% of the time. Maybe for Google, it's like 1 over a million, 1 over a billion. Okay. And that's what we want to basically try to identify, the heavy hitters in this kind of infinitely large stream. Okay. Okay. And what makes it an interesting problem, a little more formally, is that we want to use kind of sublinear space, something smaller than the data size. Otherwise, you just have a counter for everything. That's not so fun. So, might say, oh, square root n space, where maybe n is the number of distinct elements out of a total stream of length m. Per computer science tradition, we choose the only two letters that sound the exact same. But square root n would already be non-trivial, right? Because you're throwing away still n minus square root n. That's the vast majority of different elements. Log n would be, more impressive. Okay, we're going to simplify things and assume everything has an identity, integer identity between like 1 and n. Okay, maybe it's just a SHA-2 hash or something. Okay, good. So, okay. So at some level, if I pose it as how are you going to count everything without space to count everything? Okay, that just seems impossible on the face of it, right? Uh, but why might we have hope? Okay, so indeed, if we needed to do things exactly, if you really needed to count everything exactly, you can't do anything but count everything exactly. It's not hard to show, that you can't cheat here. But we're going to take advantage of kind of three, relaxations, and this will happen a lot in this class. I guess approximating 3-sat was a relaxation last class, but we'll kind of find some wiggle room that lets us do something constructive. Yeah. Okay. So actually, does anyone want to try to guess any ideas as to why we might have some hope? I'm not sure if this is a fair question. Like, I don't know if I gave you enough to work with, but yeah. We can estimate with some error. Okay, that's either A, B, or C. I'm gonna. Damn it. Well, another one is randomization. Okay, we're allowed to randomize our algorithm. Um, okay. All right, we are going to allow some margin of error, and that's really important. Yeah, if you do things exactly, then you have to do things exactly at some level. Okay. Two, we're going to have some randomization. So our algorithm is allowed to be wrong sometimes. Okay, but it'll be something that in both cases we'll make sure we analyze it rigorously. We want to be able to say precisely, look, this is exactly the kind of error you're going to get with exactly this frequency. And you can tune these parameters so you understand the trade-off. And then lastly, I think a really nice important point, although our input is much, much bigger than we can work with, the input size, our output size is potentially quite small. If you're only looking for 5% heavy hitters, for example, there's only 20 of them. Okay, so the fact that your output should be small at least gives you some hope. If the output also had to be big, I think you're really hopeless. Okay, but the fact that the output is small, it gives you some hope. The hard part, of course, is we don't know uh, which 20 we should find. So that makes the whole thing a little bit tricky. But it is good to point out that the output is at least tractable. Okay, so uh, to do this, we're gonna use hash functions in a clever way. Yeah. Okay. Okay. So hash functions, I'm sure you've seen and certainly used. I mean, I'm sure you use hash tables and stuff when you program all the time before. But let me go through it a little bit slowly since it's an important object for us. So the idea is just a map from integers to integers. But at least today, we're going to go from a big space of integers to a relatively small space of integers. Okay. And the general idea is that it should be like a kind of random looking function from the many integer space to the relatively small space. Okay. That also means, just by pigeonhole kind of stuff, that you're inevitably going to get lots of numbers that map down to the same number in the smaller space. These are called collisions. Okay. Now, I think one subtle point to make when I say a random function, you take an input, you get something out. But there's two ways to interpret that. It could be like you put in a number and then something random happens and out comes another number. But that's not what we're doing here. So these functions, we're going to construct them randomly ahead of time. And then we'll put in a number and it'll look like it's random on the outside. But it's actually kind of like fixed internally. Okay, so these are randomly constructed functions in particular. Okay, so the simplest example of a hash function would be like an ideal hash function. Okay, this is where any number can get mapped to any output number. It was kind of like anything's possible. Of all possible ways to map from n to k, we'll draw one uniformly at random. This is the easiest to think about and the easiest to analyze, right? Because you just analyze, oh, this number could be anything, that number could be anything. Okay. Often when you're designing algorithms for the first time, it's good to just start here, assume this. Because the simplest thing to work with analytically. But there is a catch. It is a little bit too good to be true. Why is an ideal hash function that's kind of uniformly random out of all these possible functions? Why is that too good to be true? Yeah. So there are a ton of possibilities. And so, look, I mean, there's k to the n because each, uh, is it k to the n or n to the k, k to the n? Okay, so each of our n inputs has a choice of k times k. Okay, but what are the ramifications of this? Ah, okay, so space becomes an issue, right? So how much space do we need? If there's k to the n possibilities, you're going to need logarithmically as many bits. So if you have like 10 bits, it can only describe 2 to the 10 different things. If you have 100 bits, it can only describe 2 to the 100 different things. So if you need to describe k to the n different things, you need logarithmically many, okay? So you need n log k bits, which is basically like for each of your inputs, just drawing a random number between 1 and k and writing it down with log k bits. So you can't compress it any further than just listing out the entire mapping, okay? And especially for us when we're working in this space where n is huge and stuff like that, this is a no-go. All right, so we can't work with that directly, although it's still a good model to have in mind. What we do instead in algorithms, and today's just the first example, is we work with hash functions that have kind of limited randomization properties. They won't be fully random in that previous sense, but they'll be random enough to get the job done. So this is almost the simplest thing that's still useful. Okay, so it says, okay, universal hash function. They call it universal. It says that for any distinct inputs and two inputs, the odds of them colliding, having the same hash output, is as if they were drawn uniformly at random, 1 over k. Okay? But it's only for pairs. It says nothing about triplets, things like this. Okay, so it's a very minimal uh, requirement. Okay? And the question we'll see in the second half of the lecture is what you can do with just this. Okay, but why is this nice? So here would be a concrete example of a universal hash function. Very simple. It's just ax plus b mod k. Mod p mod k. Ax plus b mod p mod k. Let me go through that a little more slowly. So you're gonna work with choose some big prime number p that you're kind of working in a field. It's probably to make sure that you use a fixed number of bits on your computer. Okay, and then you're gonna draw random numbers between I guess 1 and p and 0 and p minus 1. Okay, and then when you want to compute this, you just do ax plus b mod p, and that gives you some number between 1 and p, and then you project that down into your k space, so you do mod k. Okay? But clearly this is a very simple function, ax plus b. And for homework, you'll show that it has this universal property. It's a little tedious, but it's not the end of the world. I think I wrote it correctly, but I might have been off by 1. You can double check on the homework. Yeah. The question was whether this p is correct, and where I stand now, I can only say I hope so. But I will be off by, it might be p minus 1, but I think it was p. I think I checked at the time. It is a little odd. Yeah. It is p minus 1 in the homework? Okay, so it should be p minus 1. Okay. Okay, so something like that. Yeah? All right, good. Okay, so that's one thing we're going to use. The other thing we'll use is Markov's inequality. I'll do it quickly since we did it last time. But Markov's inequality, if you have a non-negative random variable, the odds of being twice the average is at most 1/2. 4 times the average is at most 1/4. Otherwise, the average would get higher. That's all. Okay, good. All right, let's go back to our fun problem. Okay, heavy hitters. Trying to find everything that appears at least 5% of the time in the stream. Okay, we want to do it in sublinear space. And instead of 5%, I'm going to use some value epsilon. Okay. So epsilon is like 0.05 for 5%. Okay, good. Okay, I'm gonna switch the problem just a little bit. We're not going to directly work on heavy hitters, although we can come back to this point if time permits. And turn into like a frequency estimation problem. So let me just define some terms. So an element's going to appear several times in the stream, or maybe just once or none at all. The total number of times it appears we'll call we'll call the absolute frequency, and then divided by the length of the stream, we'll call the relative frequency. Okay, not supposed to be too complicated. So for example, something is an epsilon heavy hitter if and only if the relative frequency is at least epsilon. Okay. So what we're going to do is we're going to focus on estimating the relatively frequency of all the elements up to say some epsilon additive error for some parameter epsilon. And then I'll leave it to you to think about, or if we have time, we can discuss at the end how to convert that into an algorithm that can gather the heavy hitters on the fly. Okay, but for first, I'm going to just transition the problem to one that's maybe a little more ambitious. Now I actually want to try to estimate the relative frequency of all the elements up to a fixed additive error of epsilon. That makes sense? Okay. Good. Okay. Still have the same issue where you don't have enough space for all the counters. Um, what's one good piece of news? So if now I'm asking you to be able to report all the frequencies of all the elements up to epsilon additive error. That would seem space demanding, except we do have an out. Yeah, so 0 is a good answer for most of the elements. Only 1 over epsilon elements it's not good for. So that's actually good news. Again, we don't actually really need that many counters potentially, although we don't know which counters uh, to keep track of. Okay, so I'm trying to count these elements. I don't know which ones to count, although in principle, I don't have to count that many explicitly. Okay, good. Okay, okay. This is supposed to be where I ask if you have any ideas. Yeah. Okay. So I'm going to just repeat it out loud. I'm going to maintain a list of 1 over epsilon elements. That'll give me a small amount of space. And then if I see an element, I'll increase the counter. And if I don't see it, then I'll just bypass it. Yeah. Oh, so that's not an unreasonable idea. So okay. Uh, let's say the first 1 over epsilon elements come in. I'll just start new counters for each. And then the next element comes in. If it's one of the things I'm already tracking, I'll increase the counter. If it's not something I'm tracking, I'll decrease everyone. But you can see at least there's some idea of trying to figure out kind of what to replace in our set. Yeah. Okay, so once my buffer is full, um, and I want to a new element comes in, I'll have to randomly kick someone out. Okay, so this okay, so I think you're referring to something called I said no name. Okay, this is reservoir sampling. So this is trying to get a uniformly random sample out of the. Oh, okay, okay. So reservoir sampling, which has appeared on midterms before, but so that's a different idea, but it's an interesting idea. So the idea is like, okay, if I can maintain a uniformly random sample of the stream of some size, then when I need to report the numbers, maybe I can just look at my sample and make some estimates based on that. Okay. Um, that will actually not. That's not such a bad idea. Would you at the top of your head know roughly how much space you would need? Well, okay, so you'll want your sample to be extra big so that you can have good statistical accuracy. I think you're going to need, I'm just kind of placing this here because we're going to do something else. I think you'll probably need like log n over epsilon cubed or epsilon squared space. It's because you need your sample to be big enough to be able for your sample to be representative of the stream. And it's either, it might be epsilon cubed. Because each of the elements are pretty small. Yeah. Something like that. Okay. This is actually not a bad idea, although it's not the direction we're going to go. I'll only briefly recap for everyone who's like, what the hell happened? The idea is, if out of the whole stream, you could in hindsight, draw a random sample from the stream of some moderate size. I think log n over epsilon cubed elements uniformly at random would be okay, but one has to double check. And then just study that and use that as like an estimate. Just like, when they're polling to see who's going to win president, they just choose random people and then extrapolate from there, right? So that's an idea. And then there's this very nice maybe we can do it if there's time at the end, but there's a nice algorithm called reservoir sampling that lets you maintain uniformly random samples online in a stream. Yeah, maybe at the end if we have time we can do it. That's sort of fun. It'll be a good practice of some of our ideas. Okay, but that's not the direction we're going to go. We're actually going to try to do better than log n over epsilon cubed as well. Yeah. So that's the nice part. It won't. It won't. Yeah. 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 Maybe if I have time, we can do it slower at the end. Yeah. Okay. So what we're going to do then is we're going to try to use hashing because otherwise, why did I bother? Okay. So So the idea is that at some level you want to maintain roughly 1 over epsilon counters, but you don't know which one. Okay. So I'm going to allocate roughly 1 over epsilon counters, maybe 10 over epsilon, a little extra. Okay. So I'm just going to allocate some array of counters. And now and construct a universal hash function. So I'll draw some random ax plus b. Okay. And now when an element comes in, element 10, I'll plug in what's h of 10. It'll take me to one of these 10 over epsilon counters, and I'll increment that one. Okay, so I didn't know which counters I needed ahead of time, but I'll just allocate some counters and just hash things down kind of arbitrarily or randomly, quasi-randomly. Okay, does that make sense? Okay, so that means like if I want to, yeah, here's maybe okay, yeah, okay. So let's say I did this. I processed the whole stream, okay, and now I said, okay, what's your estimate for the frequency of element 10? Given this structure, just to make sure we're on the same page, how might you report the frequency of element 10? What would be kind of a natural? Yeah. Yeah, we'll just look up h of 10 and return that number. That number might overestimate because other things are getting hashed in and colliding, but otherwise it's a natural answer. Yeah, did you have another idea? Uh, uh, or the length of the stream. It depends on if you're reporting the absolute frequency or the relative frequency. Yeah, so if we're reporting the relative frequency, we could divide by the total length of the stream, and we could be counting the number of elements along the way. Yeah. Is the number of distinct elements too large to iterate through to see how many collisions there are? So I think the answer is yes on multiple fronts. One, it just is too many. Like if it was all the queries, you don't want to list everything. But two, also things are kind of like coming in a stream. So you can't really go back and you don't want to like waste part of the stream. The stream itself is not necessarily in some like random order. That would actually make our lives much easier. It's in some adversarial order. So if you say, oh, I'm going to spend like the first 1/10 of the stream studying it and trying to do some pre-processing or something, you might be giving up something valuable or something like this. Okay. So so to estimate the frequency, the absolute frequency, you just return the hash counter. For relative frequency, just kind of divide appropriately. Okay, good. So that's always going to overcount. All right, so kind of simple algorithm. Don't want to lose sight of the fact that the algorithm itself is simple. Now we want to analyze it. So here's some notation. So I'll be using, I guess, A from 1 to W to refer to this array of counters. F sub I will be the true frequency. H is the hash function. M is the length of the stream. So for example, the jth counter will be containing, I'm going to sum up over all the input indices, the hash to bucket J, the true frequencies. Okay. Hopefully that's reasonable. It's on the right hand side. Okay. So now here's our first kind of, and really the main lemma. Okay. For all elements I, so we'll just focus on one element at a time, is probability at least 50%. Okay. I'll return some estimate that's between f sub I and f sub I plus, let's say, epsilon over 5 times the length of the stream. Does that claim make sense? Okay, so it's probability at least 1/2. I'll return something in this window. Okay, so that's not bad. It's a simple algorithm for all elements. Sometimes you're right. Okay, good. So we have two inequalities. The first one is this fi less than equal to a. This is the easier side. Why is this true? Yeah. Yeah, and in general, I guess the key thing is that our algorithm only overestimates because I return my own count plus things that collided with me. Okay, so that's not so bad. The interesting question is why it doesn't overcount by too much. I'm allowed, our goal is to get like epsilon m error in terms of total frequency, right? So that's about, I guess, 1/5 of that. Okay, so what might be a okay place to start, right? No, this is some random quantity, AHI, it's a bunch of collided counts. Where should we start? Yeah, we will use, yes, we're absolutely going to use this, but we got to get there. So what should I write first? It's like a nice first observation. This will often be the case for new problems. Studying some random thing. What's the first thing you want to know about it? Yeah. Expectation. Let's start with the expectation. Yeah. That'll get us going. All right. So what's the expected value of a h of I? Okay. So first I'll just plug things in. Okay. So I guess we're going to be summing over all the indices I, j, k, k, where h of k is equal to h of I. So these are everything that collided, including itself. Uh, f of k. Yeah. So I'm just kind of plugging in kind of what the definition of the algorithm. Okay, what next? Yeah, linear expectation. I think here, if you were doing it very slowly, you'd want to be kind of very careful. So, for example, you could make a random variable. Uh, so I guess what I'm saying is that the randomization is kind of hiding in the sum, right? That's what a random, because that's the colliding part. Okay, so you can do something like this is f sub k if hk is equal to hi, zero otherwise, so that you get something like the expected sum of xk over all k. Okay, and then now you can kind of properly apply linear expectation. Okay, just like a minor technical point. Okay, good. Now, what are these? Yeah. Well, I think especially since it's the first couple of classes, I want to make explicit how we're using linear expectation properly. Yeah, just a pattern match. I think that whenever you're in a situation where you kind of have a sum, if some random thing happens, add this term. Okay. In that case, you can always have an indicator variable that's kind of like 1 if that event happens, 0 if the event doesn't happen, times fk or something. So I think you can always do this. I mean, at least I'm having trouble imagining when you cannot. Okay, so all we're doing is kind of taking this sum, which sort of has like an if built into the terms you're summing over, and we're doing a sum over everything with the if kind of inside. The condition is inside. So I think the answer is yes, but it's a bit of an unbounded question too. Is that okay? Okay. All right, good. So now for any particular k, I think there's actually two cases of interest. Yeah, what do we get? So for most of those k's, most of those other elements, yeah. Okay, so f of j or f of k times the probability that h of k is equal to h of I. Good, perfect. So now what is this? Sorry? The other case? Oh no, okay, okay. So we're here now. We're summing over all the elements. For each one, with some probability they collide, and you get the count. So now what do we do here? Yeah, unfortunately we use 1 over k before, but okay, but universal, this is where the universal hash, so I was looking at you. The universal hash function part is going to come in. So now 1 over w for this setting. Um, we choose the worst variables to keep you on your toes. So you get something that looks like this. Is that correct? Oh, sure, less than equal. But also, is that correct? It always collides with itself. So we should be a little bit more careful. So let me get rid of that. Uh, f sub I plus summing over all of the other indices, uh, fk over w. Okay. Uh, and now, well, this sum isn't the end of the world, but we can make this sum a little bit simpler. kind of relate it back to our statement. Yeah. Sorry. Uh, no. Not quite. Huh? Yeah, we can just replace it with M. We'll give up a little bit. I mean, I'm kind of lazy. M over W. Okay. We're double counting Fi a little bit. You could remove that if you want. Okay. All right, so that's nice and simple. Which I should mention is epsilon M over 10 for our choice of W. Yeah. Okay. Good. So we're making progress. Let me give us some space. Okay. All right, we're making progress. But the original statement is a little bit different, right? So the original statement was probably 1/2. Uh, it's at most epsilon M over 5, which is actually a bigger margin. Okay, so I think the expectation is great, right? Because it's saying, look, you expect this much error, so that makes that window much more believable because the expected error is sitting right in between. Yeah, so now you have some grip of the situation. Okay? But now I really want to show, I want to get sort of this probabilistic event, right? Half the time I'm within this error, not just like on average I have this error. So I'm trying to go from average, saying some fraction of the time I get this error. All right, yeah. Okay, so we're going to use Markov's inequality to try to convert something about the average. Okay, and there's one trick that we're gonna want, or one not trick but like observation. So we can kind of move this fi term into that left hand side and subtract. So let me explain. So in other words, what we showed was that the expected value, the sum, let me, I'll write it like this. Sorry, of a hi, that returned value, minus fi, okay, is less than equal to epsilon m over 10. Okay. Now, to apply Markov's inequality, you can't apply to any random variable. You do need one fact about the random variable, and that is it's non-negative. It needs to be non-negative. So is this non-negative? Yeah, because it's always overcounting. Okay. So it's this term, this is actually important. It's this term that we look at the average of. Okay, and the average is at most epsilon m over 10. That means the odds of it being at least epsilon m over 5, that's twice the average, is at most 1/2. Okay. All right. So yeah. So Markov will give you the probability that. Okay, I won't even write it out. Over 5. And the point is, this is 2 times the expected value of what was supposed to be happening. Is at most 1/2. I guess the probability should have been done like this or something. Okay, it's a little messy, but by a little messy, I mean it's a complete mess. Okay. All right, but that's the idea. Good. Okay. Okay, so we've made some progress. Okay, took this very basic problem. I want to estimate all the frequencies of all the elements. Okay, and we've shown a very simple algorithm that for every element simultaneously, we'll get a good estimate with constant probability. Okay, it won't get all the elements simultaneously. For any of the elements with probability 1/2, you'll get a good estimate. Okay, now I want to start making this stronger. I want to make sure that all of my frequencies for all of my elements are good with really, really good probability. Say 1 over n squared, 1 over n to the 10, however high I want. Okay. So we have something that works for some elements sometimes, and I wanted to get to work for all elements almost all the time. Okay. Any ideas? Yeah. Just add more hash tables. It's as if you've seen this lecture before. Uh, okay. So what do you mean? Yeah, okay. So like, okay, yeah. So this would just come. Oh, that was supposed to be erased. But that's okay. Okay. So it's not super hard math anyway. So obviously the probability of getting one tail is one half. Probably getting two straight tails is one fourth. 100 straight tails is 1 over 2 to the 100, right? But the point is that it plummets insanely fast, right? Exponentially fast, right? If you flip 100 coins, like I don't know what 1 over 2 to the 100 is, but it's really small, right? So that's what we want to take advantage of, right? I mean, that's going so fast, it might get over the fact that we have to deal with a ton of elements. Okay, so we're going to make d copies of what we just did. Okay, so I'll make d sets of counters, and I'll make d universal hash functions. Okay, so repeat this experiment d times, and so the total space will be w times d. Okay, okay. So now, and so I think the algorithm's straightforward. Now an element comes in, you increment a bunch of counters. Okay, now if I want to report, let's say now give me an estimate for element 10 or something, and you have d different counters to work with. You can look up all d of them, right? And then what do you return? Sorry, the smallest one. I should mention that one natural idea is average. That's often the first answer. But actually, all of our counts are overestimates. So in our case, the smallest one will be the best estimate. So we are going to return the minimum over all the counters. Okay. And that's going to be a bad counter. I mean, bad returned value. Only if all of your counters are bad, right? If a single counter is good, then your min will get it, right? So you only make a mistake if you make d straight mistakes. And what are the odds of that? Say 1 over 2 to the d. Okay, good. All right, so if I set d to be like 10 log n, where n is the number of distinct elements out there, right? Now I'm bad with probably 1 over 2 to the d, and that becomes like 1 over n to the 10, right? Just some constant over in front of a log. But that's kind of how fast this error goes down. Okay? So now you're basically able to drive any element's error rate down as low as you want. Okay? But our goal is to try to get to a situation where all the elements are estimated correctly. So now what? All right, so now for each individual element, you're supremely confident. I want to say, okay, but now we're going to be able to get all of them. Yeah. Okay. We're going to use a union bound. So this is probably of some element E being bad. So that means, you have all these possible events, one event for every element. You don't want any of them to happen. Yeah. So by the union bound, uh, we can look at this sum. The summing up over all the elements, what are the odds of E being bad? Right? And so this is something like, summing up over all the E, 1 over n to the 10. There's only n elements. So you end up with 1 over n to the 9. Okay? So this exponential kind of drop off in error is so nice, right? Because if you just go from like, if you just do 10 log n, then you get 1 over n to the 9th. If you did 20 log n, you get, n to the 19 or something, right? It's that constant, that leading constant, which is just hiding in the big O notation, is showing up in the exponent of your error probability. Yeah. Yeah, each one will get its own hash function. Yeah. Yeah, yeah. So here, oh, well, the proof is in the other copy of the slides. But bad means that I'm not in this range. And good means I'm in the range. I mean, I'm just overcounting by too much. And since we're returning the min here, if any of those are not too big and they're good, then we'll get something that's not too big. So I'm only worried about things being too big. So the min is great. Yeah. Yeah. Okay. So how might you actually, well, okay, I only mentioned that the space is log n over epsilon because you have log n over epsilon. Okay. So, okay, good. All right. Okay. So the question is, what would you do in real life? We can open that up to, so you actually wanted to use something like this to cache items, and your kind of universe of possible things was really big, and maybe they're arbitrary strings or something. Any ideas? Yeah. Well, yeah, I guess he's concerned about n being big, or at some level, even how to get IDs for them. Yeah. So first of all, how many like atoms are in the universe? I have this in my other class. I just know that log n is 8, where n is the number of atoms in the universe. So we just have to work backwards. Uh, huh? It's like 10 to the 80. It's like 2 to the 250 or 260 or something. Okay, so like, there's probably not as many queries as atoms in the universe. But so what one thing you could do is you could take the SHA-2 or some fingerprinting hash function, which will write it down as like 260 bits, and then work with that. And then at some level, like another thing is that log n is effectively bounded above by m. We really only have to take union bound over the queries we'll see, which is bounded by m, the length of the stream. I mean, the number of distinct elements we actually see. Like even if the key range was kind of sparse, that doesn't really affect our algorithm as long as the initial hash function was kind of wide enough on the input size. Is that so here, if log n was actually the n was implicitly much smaller, that would kind of be okay for us. So yeah. Okay, yeah, so let's do that part. Okay, so that's right. So I changed gears on all of you and switched to focusing on estimating frequencies. But originally the goal was to get all the heavy hitters, the epsilon heavy hitters. Yeah. So we haven't done that yet. Okay, so we have plenty of time actually, I think. So any ideas? This might also help for your question a little bit, just getting comfortable with what's going on. Right? So you have a very cute, clever algorithm that can report these numbers, but now you actually want the heavy hitters. And of course, you can't like go back in time and look at your old stream. So you want to somehow do this online. Yeah. Okay, so let's walk through it just slowly then. So, okay, so now our goal is to actually get the heavy hitters. So what would we do so at the very beginning, you kind of have this empty tables and you probably don't have anything in hand otherwise, right? So an element comes in, you hash in the counter, then what? Okay, so maybe you kind of like take the first element, and in general, okay, so at some level, it feels like at any point in time, maybe a nice way to think about it is inductively. Partway through the stream, let's say you already have the heavy hitters in your hand up to that point, right? And then a new element comes in. You want to update your list, and maybe in the process, think about what information you needed in your list to be able to maintain this. Okay, so you're a million elements have already come in. You already have a good heavy hitter set for those first 1 million elements. Okay, 1,000,001 element comes in. What do you procedurally do. Okay, so let me just do it explicitly for everyone's benefit. So element I sub m comes in, like the index is I and the m slot. And I guess you're first going to add it to your thing, right? So you're going to add it to your counters and stuff. All right, so you're going to count it. And that's also going to give you some kind of estimate, right? You're going to get some, okay, well, based on my data structure at this point in time, I think it's appeared this many times. Yeah. And then you can take that number and so your data structure returned a count. You can add to, but what would the price? Yeah. So effectively, yeah. Okay, I'm lazier. I would just say like if this reported number is at least epsilon times m, if it's a heavy hitter right now, I'll hold on to it and I'll remember that count. You can put this all into a heap or a priority queue to do this for you. But really the point is that as the elements come in, you're counting them, right? So you have a count and you use that count to say, oh, I think it's an epsilon heavy hitter or it's not. And then maybe for the elements you already had, you maintain those, counts at the point you added it so that, at some point they drop off if they're not getting incremented. And so you also let go of some of them online. Okay. Now I do want to make one point though, which is that our data structure has error. It can be off by epsilon. So let's work through the ramifications of that, right? So for example, uh, let's say you wanted the epsilon heavy hitters, and you set your data structure with parameter exactly epsilon. Okay. But the way our data structure is set up is that we can actually get lots of elements with error epsilon. So suddenly you find yourself holding on to tons and tons and tons of heavy hitters, right? Because you get all these zero elements that somehow you gave error epsilon. Okay. So what I'm saying is that we should take our heavy hitters problem and figure out the right kind of approximation guarantee. It's going to be hard to do it as nicely as we want. And also figure out the right parameter for our data structure. Because right now to just do epsilon and epsilon is going to lead you to take all these effectively zero count elements, potentially. Right? Because we could get error up to epsilon. So what are some like natural, I'm speaking a little high level, what are some natural remedies? Yeah. Yeah, so okay, so let's say our goal is something like, I'll put a squiggly thing there, something like epsilon heavy hitter. So epsilon is fixed based on what we want from a heavy hitter point of view. Now for our data structure had its own epsilon parameter, but what might we set that value to? Yeah, so why don't we do this count min thing we just did with a parameter, say epsilon over 2. It's only twice as much space and it's hiding in a big O anyway. Okay. So now we're always going to be overestimating by at most epsilon over 2. Okay. Now, if we run that same strategy each time an element comes in, I check the data structure, see if that reported frequency is at least epsilon times m. I will get all the epsilon heavy hitters, but I might also get some x heavy hitters for what value of x. So our data structure is overcounting by epsilon over 2, at most epsilon over 2. And I'm taking anything where the overcounts are at least epsilon. Yeah, so that will lead to a list of epsilon over 2 heavy hitters, because epsilon minus epsilon over 2 will give you epsilon over 2. Epsilon over 2 heavy hitters, that includes all epsilon heavy hitters. Okay, so our data structure won't be perfect. It'll take a few extra elements, at most 2 over epsilon, so it's not so bad. It'll take a few extra elements that are at least epsilon over 2 heavy hitters. But it'll definitely include all epsilon heavy hitters. And I think it's not so hard. If you want to decrease that margin between epsilon and epsilon over 2, you could think about how to tweak that. Yeah, question. Yeah, so there's a couple different ways things we could have done. We could have made W wider, D bigger, or whatever. And the question is, uh, it's a little bit of a wash, but really, I think so. Okay, so what's driving this analysis? So here's maybe a slight reframing of your question. So at this stage, I could have made W way bigger. Let's say I make like W much bigger, and then make D proportionately less big. Okay, and if you did that, so let's say I made this times some alpha. Some alpha is 100, a million, whatever. Okay, and then down here, I'll go from D to D over alpha. So the total space will remain constant. This W times D. Okay. Now, I think if you do this correctly, so this might go down to something like 1 over 2 alpha or something, if I remember correctly. Because Markov's inequality is just this kind of like, so our average error will, go down by a factor of alpha, so that when you just take the reciprocal, when you do Markov's inequality, you'll gain something by alpha. Okay. So, and meanwhile, D goes down by alpha. So you're going to look at something like, 1 over alpha to the D over alpha is the high level trade-off. There might be a 2 down here or something. Okay. And in general, there may be, you could do the calculus and it might not be exactly alpha equal to 1. But from this so this is just keeping the total space constant and just playing with the calculations. Okay. You really want to worry about the exponent. Once you get this thing, below 1 as a constant, then you're really gaining from the exponent. So the idea, I mean, I chose just numbers to make our lives as easy as possible, just in terms of keeping the calculations clean. But really, morally, you just want this to be wide enough so the error is some constant less than 1. And you're really, really gaining from the exponent. So maybe you want to actually make this shrink it tiny. There's not much margin because we're already at like 10 over epsilon. But yeah. This will happen in a few more algorithms where there's like kind of one step where you get a modest error, just good enough that you can just ramp it up after that. Okay. All right. We still have time. Okay. So first of all, did that part make sense? And I'll give you guys 3 options, I guess. Okay. Here are your 3 choices. One, I can do the first 5 minutes of the next lecture, which is prepared. It's just starting hash tables, and then we could do a fancy hash table next time. 2, we can do this reservoir sampling that came up. Or 3, you can just leave. You can just leave anyway. You could have left earlier. You didn't have to come today. I don't. Okay. All right. So if option 3, just take off. That's fine. But out of option 1 and 2, yeah. What is this question? Oh, I thought we satisfied this. Okay. What remains? Okay, so yeah, maybe you got sidetracked. So the high level idea is we want to get all the epsilon heavy hitters using our data structure that's now very good at frequency counts. And if you did the first thing that came to mind, which is to use your data structure with the same parameter epsilon, that won't quite work because your data structure can be off by epsilon. So things with frequency essentially 0, you'll think is a heavy hitter, which means you'll accumulate a huge list and you'll lose all this kind of space stuff you're concerned with. So our tweak is to initialize our data structure. If we're going for epsilon heavy hitters, we're going to initialize our data structure with parameter epsilon over 2. So half the error. Okay. And then as we process elements one by one, I'll feed it into my thing. And based on that returned overestimate, if it looks like a heavy hitter, I'll put it in my bag. And meanwhile, I can check my bag to see if things are still heavy hitters. Okay. Now, our data structure is off by epsilon over 2, and it'll take anything that looks like it's at least epsilon. So we'll only take elements whose true frequencies are at least epsilon minus epsilon over 2, which is epsilon over 2. Okay. So at the end of the whole thing, we'll have this data structure that is taking in definitely any epsilon heavy hitter. And it might also take in some extra epsilon over 2 heavy hitters. But the good news is that, as far as the space constraint, which is the practical constraint, is concerned, there's only 2 over epsilon, epsilon over 2 heavy hitters. So we won't have too many of these things in our bag. Well, you can only take 2 over epsilon because they all add up to 1. And that'll keep things small. So you get this kind of bi-criteria approximation where your algorithm is always able to maintain a list that includes all the epsilon heavy hitters and includes some epsilon over 2 heavy hitters. We can't quite do it perfectly with high probability and so on and so forth. Yeah, but you won't have any really bad things, and you'll have some things that aren't quite as good as you hope for. And you can squeeze the difference between epsilon and epsilon over 2 by playing with parameters. Yeah. Okay, so we never showed. So here we never showed that it's so I guess we're going to do option 4, which is just keep talking about this. But so we never showed that it's always correct. All we can show is that it's going to be off by at most epsilon over 5m or something, epsilon m, with some constant probability. Yeah. And that's basically necessary. If you want to do things perfectly, then you have to do things perfectly, and then you're screwed. Any other questions? Yeah. Sure. So I might put this on the homework. So okay, can you do a more refined analysis in like nice situations? Okay, so I think there is going to be. Okay, so if you start making assumptions on the stream, I mean, if the problem is nice, then the problem is nice. But like, okay, so for example, there's one problem that will probably be on your homework. Okay, and the idea is like, okay, so what's the idea? The idea is like, okay, suppose I listed all the elements like in descending order of frequency. Okay, and there's like different distributions. You can have one distribution where like everyone's very similar to each other, and you can have other distributions that are like extremely sharp or something like this. Okay, and the homework is about these very sharp distributions, which I don't know, somebody might argue is realistic. Okay, where the mass of the distribution is coming from the heavy hitters, and let's say the heavy hitter line was like drawn there or something, and that this part down here under this curve really represents a very small part of the stream because the stream is dominated by heavy hitters for some value of epsilon. And what the homework will ask is to get the same guarantees we just did, except instead of doing an epsilon fraction of m, it'll be an epsilon fraction of this tail. Okay. And then that'll require some, I mean, there's some hints or something, but you'll do some refined analysis based on what we did, and you can get some error proportional to this part instead of the whole thing. Yeah. Yeah. Well, I think when we say that a hash function is good or bad, that's sort of hand in hand the same as other elements getting. Think of like the input being fixed, like adversary has already fixed the input, and now you're just drawing hash functions. So a good hash function is one that doesn't collide with you too much, and a bad function is one that does collide with you too much. Maybe I can make one more observation about this algorithm, which is an interesting feature. Usually, I never have time to cover this. Maybe I went too fast today. Okay, so I'll explain the setup. Okay, and you guys might be able to guess. Okay, so what we did here was we processed one stream, right? And imagine having one computer. Okay. Now suppose, and this might be quite realistic for the servers and stuff. Suppose you have a ton of streams, and a different computer is processing each stream. Okay, and they're each computer is subject to the same rules as before, small space, things like this. You can have them, you can set things up, orchestrate things ahead of time. You can get them kind of synced up in some way. Okay, but the point is you have a bunch of independent streams, and they're going to be processing and counting things, and then at the end, you want you want to be able to somehow aggregate the results and report the heavy hitters for the whole thing, or be able to do frequency counts for the whole thing. You just want to be able to do the whole combined thing while processing things in separate streams, where each stream is kind of subject to the same rules. Yeah, without writing it all down. Okay. All right. Any ideas? This will be the last thing. There's a short answer, so yeah. Okay, so can we distribute the hash table? So what does that mean? They could be completely different. Maybe this has all the animals and that has all the Pokemon or whatever. So we're not assuming that like out of the whole data, like it's all kind of nicely split up across the streams. It could, yeah. We'll make no assumptions about how the data split up. Yeah. Okay, we're gonna run it for each. Now, what does it mean to aggregate? Okay, so let's say I run something for each one and I kind of get them all into one computer at the end, and I want to look up one element's frequency. What did you have in mind? So the idea is that for each element I'll query this, query this, query this, query this, and then add them up. Okay, so that could work. Now that your overall thing, if you have 100 streams, you're going to need 100 times as much space, at this stage, right? And then a million times, a million times. Can you do better? Yeah, better than that. There's something slicker. Yeah, not quite. I still want to be able to do most of the processing independently. I want that last step to be very light because you're processing tons of data. Yeah. Okay, so instead of like kind of concatenating, or kind of, if I could say that for your idea before, can we somehow just add those tables together? Just some, then you don't have to use extra space, right? Okay, but you do need to be careful about one thing for this idea to work. We'll use the same hash functions for each of these instances. So we will run the same algorithm for each one, but we'll be very careful to make sure that each instance gets the same hash function. So you can actually just combine them afterwards by summing them up. And it'll be just as if they were all running on the same stream. Yeah. Okay, so this is very nice. So this is a powerful idea in big data algorithms. It's called sketching. Okay. So whenever you have one of these algorithms or just kind of like filling out a table with some hash functions or something like this, you have this possibility of just adding things up as long as the independent instances are kind of synchronized in terms of their underlying randomization. And then you could start, processing tons of things in parallel for free. Okay. All right, good. That covers that. Went over. Sorry. Bye.